Greetings, statisticians. This is Dr. Schulman. Just thought I'd make you one. I know it's in the evening, but I was grading a bunch of your stuff and I saw some people messing up. So thought I'd make this video, which is nice. And hopefully it's clear. Hopefully this video is clear about everything that we need to do for measures of central tendency. Nope, I lied. It's for measures of variation. So I'm gonna do standard deviation. Do some standard deviation stuff. Hopefully it's clear. If it's not clear, shoot me an email. I'm gonna do it by hands. I'm going to do it on Excel, and I'll show you all the different ways. So I'm gonna share my screen, and hopefully this stuff makes sense for you. So guess what? Here we go. So let's begin. All right. Dun, 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 dun. Okay, so modules I'm going to be doing right here. We're going to be doing three. Whoa, that was fast. I'm going to be doing 3.2, this piece. Notice that you also have an article review. I'll go over that as well. But for right now, we're just going to do 3.2. It's got a lot of problems. I'll also look at the textbook, so it might take me a while, but I at least want to show you how to do this by hand. So when you just type in standard deviation, you know how it works. So let's get after it. So here is the notes, measures of variation. And I'm going to close this over, and I'm going to do standard deviation. This is the most commonly used one. It's used because we have to figure out a standardized distance between all of these points. How far does each data point separate from the mean? So here's the first formula, standard deviation. And this one looks like this. It is the summation. Now, I know I talked about summation before, but I'm not sure show you what it really means. This is always the start number. That's what this little part stands for the symbol. So this is kind of where we start. This is where we end. And that's the formula. The formula goes in the middle. So every time you see the summation, it could be from like -1 to 5, and it could be like 3x minus 2. You would put -1 in. It'd be 3 times -1 minus 2. That's the first one. Plus 3 times 0 minus 2, and all the way up until 5. So that's really what the summation means. It's adding up whatever's in here. For stats, we don't really have these parameters because it's just assumed, but usually there's numbers here and here. So let's keep going with the formula. So it's going to be the summation of x minus x bar. Then we're going to square this. We're going to divide this all by n minus 1. And then we're going to take the square root of the entire thing. Now, each one of these moves has a meaning. Each one of these things means something. And I'm going to show you what each part means as we go through it. So here it is. Here we go. So I'm going to make up some numbers. So this is for a sample. And then we also have one for the population. And if we have it for the population, it's basically the same formula. But because we have every single term, we just divide it by n. That is the only difference between working with the standard deviation of a sample versus the standard deviation of a population. Now, just to make sure I didn't mess it up, since I haven't done this formula in a minute, I'm just going to look it up. Because I never like making mistakes. Okay. So they've got the n up here, the first term. Okay. So I guess I made one little mistake. So notice how we use the x bar for the sample. I forgot to use the mu for the small mean for that population. So I'm going to change that. So one little mistake, not a big one. I just used the wrong terminology for you. Nothing crazy about it. All right, so we're gonna make up some data. I guess some small data. I'm gonna show you step by step, every step of the way, and then I'll show you using Excel and the other one that it works. So it's been hot, so I'm gonna pray for snow. So we're gonna use snow. So let's say this is the snowfall. We've got I don't know, 0, 2, -1. Oh, wait, can't have negative amount of snowfall. Sorry about that. So we got 0, 2. These are the days it snowed. 2, I don't know, 4. One day it's a 1. 1, 2, 3, 4, 5. Let's do one day that it's like 6, or we'll do one day it really snowed bad, so 8. This is the amount of snowfall in inches. So no snow, 2 days of snow, 2 inches of snow, 4, 1, and 8. This is our terms. Okay, nothing too crazy. So I'm gonna make a little table. The first one is the X. That's every one of these snowfall. So 0, 2, 2, 4, 1, and 8. That is the first part of my chart. Now I need X bar, which we know is the mean. We did it before. How do we find the mean? We add them all up, and then we divide by how many we have. Remember, the mean, in our case, is going to be from 0 to 8, or whatever n is. Or you can say it's from the first term to the nth term. And then it's just going to be x, and then we're dividing this by n. But in our sense, it's just 0 plus 2 plus 2 plus 4 plus 1 plus 8. And this is divided by how many terms did I come up with? 1, 2, 3, 4, 5, 6 terms. So we're dividing it by 6 at the end. So 2, 4, 8, 9. 9 plus 8 is going to be 17. We're just going to divide this by 6. So I have the little calculator here just to make sure I don't make a mistake. Here's our little calculator on the side. I'll put it in the middle for now. 0 plus 2 plus 2 plus 4 plus 1 plus 8. And I'll show you really exactly what this means. And we're dividing this by our terms. 1, 2, 3, 4, 5, 6 divided by 6 terms. And we have a mean of 2.83. We're going to round this to be 2.8. So this symbol means approximately 2.8. So here we go. 2.8, 2.8, 2.8, 2.8, 2.8, and finally 2.8. All right, so the next part of our chart, here we go. It's going to be x minus x bar. All right, so we have to subtract all these. All right, so 0 minus 2.8 is negative 2.8. 2 minus 2.8 is negative 0.8. 2 minus 2.8 is negative 0.8. 4 minus 2.8 is a positive 1.2. 1 minus 2.8 is going to be a negative 1.8 minus 2.8 is going to be, well, again, if you get confused, let your calculator do the work. 8 minus 2.8 is a whopping 5.2. Now, the reason why we have to square this, because if I sum these, and we could have this little be our little baby sum at the bottom. If I sum all these, I should get 0. Now, why is that crazy? Because they're all, each one of these is basically, each one of these things is how far each decimal point is from the mean. We're trying to figure out exactly how far each one of these varies from the mean. So if I add them all up without this here, guess what's going to happen? I should get a 0. So negative, 2.8 negative plus 0.8 negative plus 0.8 negative plus 1.2 plus 1.8 negative plus 5.2. I got a 0.2. So I messed up somewhere. Guess what? We're all human, right? We're all human. We all make mistakes. So I got to figure out the one little place I messed up. So that's negative 2.8. Okay. So I can just do them all again. All right. Oh, it's because I rounded them all. That's why it's not perfectly zero. It's not perfectly zero because guess what? I rounded this, but all of our numbers are right. If I had 2.83 here, for all of them, I'd get a point something zero, but that's okay. It's so close to zero, it's fine. So now we do x minus x bar, and we're going to square them. Why are we going to square them? Because that way we'll get a real value. We're not just going to be dealing with 0.2 with some negligible amounts. So, and it makes all the terms positive. So when we add them up, we don't basically have a zero up here. So here we go. 2.8 squared, or times 2.8 is 7.84. Point 8 squared is 0.64. That's also 0.64. 1.2 squared is 1.44. 1.8 squared is 3.24. And 5.2 squared is 27.04. Now I have to add them up. So here's the summation piece. X, well, we can put it right here because this is our summation because we're adding all these up. So it's x minus x bar squared. So our summation is we just have to add all these terms together. So it's 27.04 plus 3.24 plus 1.44 plus 0.64 plus 0.64 plus 7.84 is 40.84. Okay. Now all I have to do is take that value and do what to it? Divide it by n minus 1. Our n here, this should be a capital N. Sorry. Oh, that was ugly. That was real ugly because the total is all of them. All right, here we go. It's like everything being correct. All right, so our n is 6 terms, so 6 minus 1 is 7. And that's also called our degrees of freedom. We'll get there. We'll get to fancy degrees of freedom. The number on the top is 40.84. So when we divide this by 5, 8.168. This is a special number. This is called the variance. This shows you exactly how much it varies. That variance is really useful, but it's not standardized because we cheated. We did something to our numbers to like make sure that this wasn't just a 0.2 at the end, right? We did some sort of little cheat move, right? We did like a little bit of a cheat move to make this not just a 0.2, like because it was too close to zero, so we wouldn't really have any values here. So what was that cheat move? We squared everything. That's why to get the variance into standard deviation, all you have to do is take the square root of the variance. And that's all we're going to do. I'm going to take the square root of the variance. Just going to square root it. Our standard deviation is 2.86. We'll see how close we are because I rounded. the mean to make these numbers look a little bit easier to work with. But basically, I'll show you a picture of exactly what this means, which is kind of cool. So let's say this was our data. It's not really our data, but that's fine. We have a mean of 2.8. And this means every standard deviation to be one standard deviation away. We're going to add 2.86. We're going to subtract 2.86. And that means that 68%, or can't really remember exactly, was it 64%? Sometimes I make a little mistakes. Remembering it all off the top of your head sometimes a little weird. No, it was 68%. I just like to make sense. So basically what this means is 68% of our data falls between, I'll give you the exact number. 68% of our data is going to fall between, well, it's 2.8 plus 2.8. So what is that? 5.66. And we're going to subtract this and basically negative 0.6. So this means 68% of the time the snowfall is going to fall between here, which is negative 0.6 and 5.66. Can be bigger, probably can't be smaller because negative's weird. I guess snowfall wasn't the best choice. But if we go 2 standard deviations, be 94% of our scores is going to fall outside of that. So it's just a standardized number to show you the percentages of how far the numbers fall away. I'm sure I could show you different examples of this, but I want you to see that by using Excel, it'll do it right for us. So let's use Excel. Doesn't matter which Excel we use. I'll use this one. Doesn't really matter to me. And I'm going to show you how fast we know how to sell. Here we go. So here's our values. So we know this is snowfall. And we've got 0, 2, 2, 4, 1, 8. And let's just do equal average, just so we can get it. Boom. So 2.8333. Yeah, that's exactly what we got. Now we're going to do basically, here, actually make the chart. So we'll do them all. And then we know that this is here. Oh, so I have to write it 2.8333, whatever we want here. Okay, so this is going to be our mean. I can't really write X bar, but if I drag it down, it's going to match. Boom. Now I'm going to do this one, X minus mean. So I'm going to do equals the first column minus, oops, 2 minuses, the mean. And we're going to drag that down. Now, if I sum this, you'll see it should be 0. So let's just hit the sum button, watch it turn into 0. Just so I can prove I'm not like a big liar, okay? Because that's not who I am. The good thing about math, we always get the right answer, right? Isn't that fun? So we want to go to home. I don't have enough info here, so here's the sum button. Boom. 2 minus 0.0005. If we want to look at it as an actual value, a number, it's going to be 0. Isn't that nice? All right, so let's square these. So X minus mean, we're going to square them. So I'll just do a little caret with the 2. So that's what this one is. So basically, I have to take all of these subtractions and square them. So equal the first one times itself. So let's see if this will give me the second one times itself. Nice. The third one times itself. Nice. The fourth one times itself. Nice. The fifth one times itself. Nice. And the last one was a big number, right? 26. Nice. Yeah, it's a little off because I rounded, but that happens. All right, now we need the sum of these. So I'm just going to sum these. I should get a value. There's our value. And the last step, all we have to do is take this number and do what? Divide it by 1, 2, 3, 4, 5, 6. So there's 6 of these. So I just have to do 6 minus 1, so divided by 5. That's the 8.166. And so this is your variance. And then finally, to get your standard deviation, all I have to do is take the square root of this. So equals square root of the one above us. 2.85. How close was I? I got 2.86. Off by 1 decimal place. Oh, if we round it, it's the same. Look at that. Math in action. Now, if you want to cheat sheet and not do any of the steps, you can just type equals standard. Sorry, I'm a liar. STDEV. Now, you see how it says .p here? That's for the population, but we want it for the sample. So we click .s. So STEV.s. And if I grab all of these, it should just spit out what number? 2.86. And we're off. Standard deviation sample A2 to, oh, I forgot the last one. See, I forgot I did A6 instead of A7. So guess what? Let's put the A7 there. I was 1 short of my numbers. Boom, exactly the same. We've got the match. StatCrunch is the same thing. You can literally just click the key when it happens, but that's how you do standard deviation. I know I showed it before, but basically, let me give you another example of standard deviation before we do the problems. And I hope that was useful to see, but here we go. Now, standard deviation. So let's say we have a normal bell-shaped curve. I actually want a really big one, so I'm going to make a big one. And hopefully I can make this really clear for everybody what this actual math thing is that everybody seems to mess up. All right, so here we go. So let's say this is our mean. Let's say an average female's height is 5'5". Actually, let's not do height because it's in inches and it might confuse people. So let's say the average IQ score is, or let's say the average grade in this class is going to be a 75. 75% from last semester. Okay, 75 people got C's, not a big deal. And they said we found the standard deviation was, let's go with 7 points. So what does that mean? So if this means how people vary from their scores on average standardized is 7 points away from the mean, from our average. And this is for just people in one class, so we're just going to call this X bar. It's just a sample. Okay, I didn't get every student, just the students I got. So here's the first one. So this is plus, sorry, this is minus 1 SD. And this is plus 1 SD. So that's 7 points. What's 75 plus 7? That's 82. What's 75 minus 7? If you get confused with anything, let the calculator just be your friend, right? Don't freak out about it. It's 68. So this means 68% of people scored between these two. If we go one more standard deviation away, so minus 2 standard deviations, there we go, plus 2 standard deviations. Now we're at what? What is the exact percentage? Now we're at 95% of the students. So 95%, if we go here, this means we're at 95% of our students, because we almost has everything, right? Scored between what? A 61 and an 89. Now, if we go 3 standard deviations away, okay? So now we're at 99%. Okay, we're at 99%. That should be a 3. It's almost everything, right? Now, what's 7 plus 89? That's between a 96 and 61 minus 7. Remember, if things get too confusing for you, just let the calculator be your friend. So 68 minus 14, it's a 54. This means 99% of everybody scored between a 59 and a 96. That's what it means. That's all standard deviation means. It's trying to figure out exactly how far these values are. How much do people vary around the mean? Now, I hope this was clear. That's where the numbers come from. That's the formula. We had every kid in the world, or every possible day of snowfall, we use the n here, and that's the mu. But the only difference, we're not subtracting one. That's the only difference. So let's look at the book and we'll try some problems, but we're in 3.2. So here we go. 3.2. I'm going to go to my math lab. All right. So let's go to the eText, Pearson eText, and let's look at 3.2. I'm sure it's got some stuff. I'm sure it has range. I'm sure it's got a bunch of other things, but standard deviation, I believe, is the most important part. So we're going to 3.2, measures of variation. Let's see what we got. Okay. Both include formulas or computation, but not spend too much time memorizing the formulas. Instead, focus on understanding and interpreting the values. Cool. So, visualizing variation. Okay. So we've got these plots or this frequency to visualize a property of variation and look at these two data sets. This one, everybody's falling in the middle. Everybody's close, and this one's way more spread out. This means everybody scores the same. Everybody, regular Coke volume, boom, boom, boom. And then this is a special Coke volume. They're all varied. That's what this means. Both of them have the same mean of 12.2, but this one is very spread out, and this one is very close together. So guess what? This one's going to have a much bigger standard deviation or much more variation. So it's have much less variation. You want to be consistent. It's really the idea of a difference between accuracy and reliability. I think that's a really good concept. So I'm going to show you that and hopefully it'll help you. So let's do another picture. So we're playing darts. We're going to have 4. Oh, that is an ugly looking dartboard. 1, 2, 3, 4. So we got some dartboards here. I'm not the best, but here are my dartboards. Hopefully this will make these ideas like kind of more clear. I want to talk about and then I'll put different colors of darts. We'll go red. So here's the first one. Boom. Oh, we're hitting that target every time. We're right around the target, but we are not consistent at all. Here we're away from the target, but we are consistent. We are hitting that dartboard. And here, I can't hit a bullseye to save my life. So these 4 pictures really show you the difference between something that's accurate and something that's reliable. All right. So the word accurate, you can think about actual value. If we get this actual value, it's just going to make sense for us because it's what we're trying to get, the real value we are trying to get. And when they're saying reliable, it's just repeatable. Okay. We're getting the same thing over and over again. These two are not the same ideas. You might think accurate, reliable, the same thing. So let's just think about a scale first. So let's say I weigh 160. I get on the scale and I weigh 160 and it says 102 pounds. So, okay. I get on the scale again and it says 102 pounds. I'm like, all right. Get on the scale again, it says 102 pounds. That is a reliable scale. It's repeatable, but it is far from accurate. All right, so let's try it again. So let's say I still weigh 160. I get on the scale. It says 163. Okay. Then it says 159. I step off. I thought I might say something. I get back on. It says 161. This is a very accurate scale, but it is not reliable. So accurate really means the actual value, and reliable means repeatable. So this one, this first one, we're hitting the same thing and it's on it. This is accurate and reliable. This one, we're pretty accurate. We're close to it, but are we reliable? No. So this is accurate, but not reliable. Okay. This one, we are reliable. We're hitting the same point, but are we accurate? No. So this one's reliable, but not accurate. And finally, this one's neither. Not reliable nor accurate. Hopefully that helps you visualize what these words mean, especially when we're trying to think about these ideas. All right, let's get back to the book, the exciting book. Oh, we got range. We didn't do range. Range is the biggest minus the smallest. So let's go back to our data set. Our biggest was 8. Our smallest was 0. So the range of this guy, just so you got it, the range here is 8 minus 0. It is 8. Beautiful. I knew that one would be fast. It's sensitive to extremes. Yes, an outlier will throw this all off. All right. And here's standard deviation. All right, so they're using S for the sample. Oh, yeah, and that's the symbol they want to use. Cool. So I'm changing the symbol. So for instead of SD, they're just everybody is a little bit different. So their standard deviation, because there's so many things in math that are S. So there's S, and they're using this symbol, this Greek letter for their symbol. And I'm totally fine with it. They can use whatever one they want. Let me make sure I don't mispronounce it. Shortcut formula. I already hate it. We're not going to look at the shortcut formula. They don't even pronounce it. Great. Well, we can just call it, it's not a theta, but I'll look up the exact pronunciation of that Greek letter for you. Sample standard S is a biased estimator, which is explained in part 2. All right. Standard deviation can never be negative. That makes sense. It can be 0 when all the data is the same. Larger is more variation. It will increase dramatically with outliers. Yeah, no, that makes sense. Oh, I like it. Cool. So they did all the steps. But we know, do we have to all the steps? No, we can literally just take these values, whatever they are, whatever these values might be, right? Whatever these values are. Let's see if I can copy them just for fun. And we can just drop them in to Excel and just do SD sample or stdev .s for sample. I think this was the one I was on. Yeah, let's see if this works. All right, well, it won't let me do it, but ready? I've got speed 50, 25, 75, 35, 50, 25, 30, 50, 45, 25, and 20. All right, so we got all these, right? If I just do equal stdev.s, I just grab these guys. Boom, 16.55. Let's see what they got. 16.6. Ta-da! Same exact thing. Magic. So hopefully that makes sense. I hate messing with formulas. I think it's annoying. Can do it by this weird method, but I would not agree with it. Okay, so this one is strange. Now, this rule of thumb, I'm not a fan of it all. Simple 2 for understanding and interpreting standard deviation. It's based on the principle for many data sets, just 95% of it. So basically, the rule of thumb is they're just cutting it into 4 spaces. That's all that they're doing. I've never really seen it before. I started looking at Pearson. They love this rule of thumb thing, but basically they're trying to figure out significance here. So the rule of thumb is basically seeing if we're significantly high or low in values. So significantly low values are the mean minus two standard deviations, and significantly high values are the mean plus two standard deviations. And the values that are not significant are all the ones between two standard deviations. What does this mean? We only care about the middle. We do not care about this 99% that's out here. We just care about two standard deviations within the mean. That's their rule of thumb. I don't think it's great, but it's okay. Caution. Okay. And this is how so this is their formula. And we'll see how off it is for my example and this example because I hate it. So everybody's different, you know. I think this never really works out, but guess what? I'm gonna teach you to anyway. It's in the book. So you ready? So here was our numbers. We have our range. Our range was what? 8. So to get the rule of thumb, all you have to do is take this range and guess what? Just divide it by 4. Now, 8, so, and these little things means approximate. So basically it's the range divided by 4. So what is 8 divided by 4? It's 2. Our value was 3. Our value was almost 3, right? Isn't that kind of crazy how off it is? So let's do it here. Let's get the range. So this is equal to the biggest number, which is 75, minus the smallest number, which is 20. Okay, 55. Then all I have to do is take this number and divide it by 4. Let's see how close this one is. This one's off by 3, right? Like, isn't that kind of crazy? Like their standard deviation, this rule of thumb business, I feel like you lose a lot, but all I'm going to show you is what's in the book. Where we're losing it, we're losing data, we're losing information. Like, I think they came up with it because they think this formula is too hard for you guys. That's my own personal opinion. And so they want to just be like, oh, just take the range and divide it by 4. I'm not a fan of it. But guess what? Still going to show you it. I'll still hopefully make it clear. All right, let's see what else we got in this crazy book. To roughly estimate standard deviation from a collection of sample, use this. So 40, 74, and the rule of thumb to find the limit separating that from significantly low to significantly high. So I like using this idea. So we just take it, minus 2 times that for the lower. We add 2 times that for the higher. This is smart. I like this idea. But just this getting this roughly estimate business, I hate. But this part is kind of interesting. Cool. Now, if we have the whole population, the only difference in the formula, if there's no -1 here, that's if we had everybody. Okay, so what is the variance? We go back to any of these ideas, all right? So the variance is just before we square root it. Before we square root it, this value, right, which is the summation of all of our terms minus the mean over the amount of terms, that's your variance. It's before it's standardized. That variance is it's a value for how much it varies. Why do we standardize it? We standardize it because it's more similar to the values we have. It like links into the numbers we have. Instead of a measure of variance, it actually relates it to these numbers itself. Because if we were going to separate these values, 8 just seems like a lot. We can't draw this pretty picture with the 8. You know, we just can't draw it. It would go too far away. It doesn't give us the information. We cheated by square rooting it. So that's why we cheated by squaring it. So that's why we have to square root it to get rid of it. All right. I think we're ready for problems. I mean, I'm ready for problems, but I'm going to keep trying to go slow. Just let me know if I'm going too fast. Okay, some symbols. That's cool. It's an I don't know, but okay. Okay, we've got the mean absolute deviation. Y divided by n minus one. This is important. It's basically saying that we don't have every person. So we're like not constraining it. So it'll be a closer estimate because we don't know the exact number of people we have. And this is what I kept saying about the standard deviations. Their picture's a lot prettier than mine. What a surprise. They use the IQ score, which is cool. And we got something different. Okay, let's see what this stuff is. All right, let's find this theorem. So another concept helpful in understanding standard deviation is this guy. I bet he's Russian. They ever give you a person, we got to see who they are, what they look like. So let's find this guy or girl. Maria Agnesi. She was like 11 and she wrote the whole book on calculus. So there's some really great mathematicians who are girls as well. Let's find this guy or girl. That is quite a beard. Let's make sure it's standard deviation. Let's see. Make sure it's the same guy. So it's 1 over 1 minus k squared is used to find the minimum proportion that occur within a certain number of standard deviations from the mean. Cool. In normally distributed data, 68 or 1%, 95 or 2 standard deviation states that in any probability distribution, the proportion of outcomes lie within k standard deviations from the mean for anything that's greater than 1. That's nice. So we count. So how does it work? Let's check it out. Is used to find the minimum proportion of data that occur between a certain number of standard deviations from the mean. Okay. So we know that 75% of the data must lie between 2 standard deviations. Okay. The theorem gives us a minimum proportion of data that must lie. However, the true proportions found within are greater than the theorem guarantees. Okay, I like it. They got some practice questions. I'm assuming we just use the formula. We have the mean, the standard deviation, sort the data. Cool. All right. I haven't seen this one before, but I think it's interesting as usual. So it's 1 minus 1 over k squared, where k is a positive number greater than 1. For k equals 2 and k equals 3, we get these things. So I might as well show you how they got this. 75% lies within 2. All right, let's check it out. So we have 1 minus 1 over k squared. So for 2 or 3, we get the constant. So let's try 2. So 1 minus 1 over 2 squared, right? First thing they're saying for 1k is 2. And k is the amount of standard deviation. So let's figure it out. So 1 minus 1 over 4. What is 1 minus 1/4? 75%. So what does this mean? Pretty interesting. So for 2 standard deviations away, we've got 75% of our data. That's pretty cool. All right. We've got 100 and a standard deviation of 15. What can we conclude from this theorem? So let's figure it out. So we've got 100 standard deviation of 15. So at least 3/4 of the data, the 75%, are 2 standard deviations from the mean. But what is 2 standard deviations from the mean? What does that really mean, right? That's the whole idea, right? I always need this little picture. So if we know, this is 100. 1 standard deviation away is going to be what? 115 and minus 15, 85. But we're talking 2 SDs, and we know 2 SDs is 75%. So this is going to be between 130 and what else? 60. I'm assuming that's it. Oh, sorry. 85 minus 15, that's 70. But then the brain doesn't work. I'm assuming that's the answer, right? Dun, dun, dun. least 3/4 are between 70 and 130. We got it. Isn't that exciting? Okay. We got a couple more. So it's good practice to compare standard deviations when sample means are approximately the same. Comparing samples, populations, very different means better to use the coefficient of variation. They also use the coefficient of variation to compare variation from two samples or populations or different scales or units, such as heights and weights. Cool. So we got another new thing, which I'm excited about. So here we go. So the coefficient of variation is non-negative sample data expressed as a percent. So we just take the standard deviation, we divide it by the mean to get this coefficient of variation. I haven't seen this in a while. So coefficient of variation, and they call this thing what? CV. So basically, if we have a sample, it's our standard deviation over our mean times 100. That's all it means. So every time we want this coefficient of variation, we can take our standard deviation. And this way we can compare different values. Like they used heights and weights, which is pretty good. We can do like study time and grades, right? One's in seconds, one's in percentages for grades, right? So if we want to compare those standard deviations, we can use this CV idea. And that's over the mean. And we times it by 100 to just make it a percentage. That's pretty cool. Courtesies. All right. Oh, well, we made it to the end. I even learned 2 formulas on here too. So let's do 5, 8, 12, and 13, or as many as I feel like. Let's start with number 5. So here we go. Here's number 5. I lost it. So starting with number 5, let's make it happen. Range of rule of thumb, thank God we're skipping that. Number 5. Find the range, variance, and standard deviation. Nice. Include the appropriate units such as minutes in your results, blah, blah, blah. Super Bowl jersey numbers. Oh, it's like the same thing we did before. Cool. So here we have them. 12, 26, 46, 15, 11, 87, 77, 62, 60, 69, and 61. Now, can we do this by hand? Yes. Should I use StatCrunch instead? To be honest, I'm not the biggest fan of StatCrunch. I've got Excel right here. I think I'll use Excel. I will use StatCrunch in the next one, I promise. So let's make this happen. 12, 26, 46, 15, 11, 87, 77, 62, 60, 69, and 61. First thing I always do when I have stuff like this is I order the data. Why do I order the data? Just makes it look like something I can work with. I'll just do equals standard. Sorry, stdev.s. I bet that's not every player on the team, right? Doesn't look like a whole team. There was like 60 players on this team. Yes, I'd use it. So there we go. There's your standard deviation. I'm gonna put SD. Weird. They just want an S sample. Let's also get the range. Oh, we can get the variance, but they want it S squared. So I'm gonna do S with a little one of these. Just know this stands for standard deviation. And this stands for variance. And this one's gonna be range. Range doesn't have a fancy thing, but I can put an R here. So here we go. All I have to do is square this. So equal the one above times, times the one above. There we go. There's our variance. And our range is just going to be equals the biggest minus the smallest. And these are the player numbers. Boom. We got it. So these are your answers. And you can just copy and paste it into your whatever you're going to submit to me. Hopefully that was fast enough. There you are. Cool. All right, let's do the next one. What do the results tell us? There's a lot of variation. There's tons of variation in the numbers of players. It's a huge number, so that's what it tells me. Okay. Well, that was number 5. They want anything else? Nope. All right, let's do the next one. We made it to number 8. So let's do number 8. All right, number 8 says the data listed below are estimated dollars income of students who graduated from the University of North Carolina after majoring in geography. Data are based on graduates from the year 1984. Okay, total income of basketball superstar Michael Jordan, a 1984 UNC graduate, is included. Does his income? Yes, of course. Obviously, Michael Jordan's freaking salary or income is gonna far outweigh all these other people. But what do we have to do here? Find the range. Okay, it's gonna be a huge range variance. It's gonna be ginormous, way bigger than this one. I thought this one was big. This one's gonna be ginormous. So, just gonna do it again. Actually, I should use StatCrunch. I know I said I wasn't gonna do it, but I'm gonna do it. So here's StatCrunch. So I always want to show you with everything. It's just so I'm making sure I'm showing you every possible way to do these questions. So we're talking income, estimated income. All right. Let's put them in. Here's the first one. 17466, 18085, 17875, 19339, 19682, 19610, 18259, 16354, and this is Mike 2200000. Boom. All right. So all I have to do with this is go to summary tables. We want a column here, the income where you want. Remember it's control to get rid of it. So and we'll take mean, standard deviation. We don't need standard error. We'll take the median and the range too. We do not need the minimum. We do. As soon as I click another one, right? I'm putting more stuff in here just because I can. Yeah, that's fine. So we hit compute. Here we go. So the mean is 26,000. Boom, boom, boom. Now look what happens if I do this again without Jordan, right? Just see how different this is. Cool. So I'm gonna do it one more time without Jordan, just so you can see the difference. So let's go to summary stat columns. I want them both. So variable 2 is the one without Jordan. I hate standard error. All right, cool. Oh, we can find the coefficient of variance too. That's pretty cool. All right. Notice the mean. Notice the variance. Notice the standard deviation. Notice how much less this is. To me, this shows you everything you need to know. All right, so let's copy this table. We'll drop it right in for 8. Boom. Yes, look how much of a difference it has on the results, right? This e to the 11 means this is 5.2. times 10 to the 11th. That's how much variation it is between these two. It's freaking wild. And the range, whew, the median's still the same. So that's why, man, that central tendency doesn't really give us the whole picture. All right, so we did 5 and 8. What else we got? 12, 13. All right, let's see what 12 and 13 have for us. Cell phone radiation. Is it the same stuff? All right. Listed below are the measured radiation rates in watts per kilogram responding to cell phones. The data are from the Federal Communications. Are any of the results helpful in selecting a cell phone for purchase? Ugh. Well, just looking at this, I'm like, I better get this HTC Desire for the less amount of radiation, but I don't know. I guess that's up to us. 12. It's like the same thing. I just did it twice. Use Excel, use whatever one you want. I'll skip this. I'll see if there's a harder one. I'm gonna look at I'll look at 13. If 13 is the same, I'll do 12. See what 13 says. 13 is the same. Are the statistics representative of the population of all cans? It's the same. Good. So basically, the harder part of this is you've got to make a judgment call, right? You got to really make a judgment call. Caffeine measured by these brands, like so many have 0. Isn't that interesting? Are they representative of the population of all cans of the same 20 brands? Yes, I believe they are. I believe that this is just one can from the 20 brands. I bet they match up completely. But that has nothing to do with the question. So I might as well just get the answers for 13. Or 12. I'll do 12. You got you got a couple to yourself. This will be the last one I do. So I'll use Excel. More of the switch back and forth. All right, so here we go. So I got 0.97. Oh, that is not a number. 1.38, 0.93, 1.52, 1.37, 1.09, 0.48, 0.65. All right. So let's get it. So this is not every single one, so I'm just going to use the S squared, sorry, the little s squared, and then we need the range. So let's find the standard deviation. I bet it's not every phone out there, so that's why it's not the population. So STDEV.S. Boom. All right, so that's your standard deviation. And then to get it, it's so minuscule, maybe it doesn't matter, right? I think that might be the way it says. I think these are representative of the population. It's just it's probably like a regulation, just from 0.5 to 1.5. Like that's probably just what it is. So try to explain that. The range is the biggest. Our biggest, the 1.52, which is 1, 2, 3. It's the 4th one. So what phone is that? Just so you guys are aware. iPhone X, iPhone 7, the Samsung Galaxy S8. Ooh, I don't know. It's got a lot of radiation. And then we're going to minus the other one, which is the smallest one, was the last one. Oh, wait, it wasn't the last one. 30. Second to last was the LG G3. That's the one you should get. The range is super small. So here's the answer to that. Oops. I think because they're so small that it had a difference. That's what I would say here. All right. You got a few to try yourself. I did 5, 8, 12. Maybe I'll look at 21. Maybe this one will be more challenging. All right, yeah, I'll do one more of these. Find the coefficient of variation for each of the 2 samples. Then compare the variation. Nice. I'll do one more of these. So I'll do 21 as well. I always want to leave you stuff to do, but I don't want you to like freak out, not know what you're doing. So here's 21. We've got this data. And remember, this is not everything. This is not the whole thing. This is not everybody, right? This is just a sample. It says a sample. So that's why we have to know that our CV is going to be the little s over the x bar, right? CV for the other one is going to be little s over the x bar. Basically means your standard deviation over your mean. And we're just going to compare them. Oh, sorry, it's percentage, which means we have to add the 100. That's it. That's how we can get these. So I'll open a brand new page over here, and I'm going to call this syst and dias. We're going to drop them in. 118, 128, 158, 96, 156, 122, 116, 136, 126, 120. Boom. And our diast is going to be 80, 76, 74, 52. I probably should use StatCrunch because they have it in there. And I don't think this one does, but I'm already here. So it's just the way the worm turns, 72 and 82. All right, so first let's get the means for both of these. So let's get the mean. Whenever I'm doing stuff like this, I like making a table. I feel like I need a table. So I'll make myself a little table. We're gonna put boxes around it. And the first ones are gonna be grayed out because this is gonna be what we have. Oops, did I really just lose that? All right, here we go. So this one's gonna be the systolic. It's gonna be the diastolic. And we're gonna do, all right, so we need the mean, which we know is X bar in our case, right? We could put a little X bar next to it. So we know what they're talking about. And we want the standard deviation. I'm just gonna put SD, but they like what S, and then they want the range. Oh wait, no, then we just have to divide them to get the CV. So it's division, so it's X bar over S, and then the last one we just have to times by 100. So that's your CV. This is like every step of the way. Why do I make little tables? Just to make it easier for me to see. So the first thing I'm going to do is equals average, right? $127.6. All right, now I'm going to do equal average. $73.7. Cool. All right, now I'm going to do the first one, which is equals stdev.s 18.61. I'm going to take the whole thing. Oh, I have to write it again. It happens. 18.61421. So we're going to be dividing it too. So equals 12.5437. Now, what is this one? Well, this one we're going to do the division. So we're just going to do equals this times this. Boom. And because we have it in Excel, I can just drop it. Boom. And now all I have to do is take these and times them by 100 to get the other piece. So it's going to be this guy times 100. That's the percentage. And I can just drag this down. Boom. So these are your two answers. You can write a little percent symbol if you want, or you can just specify that these are in percentage by putting percent on the top. Nice. But these are the ways to compare the two values. So obviously, the difference in variation is going to be what? Way higher for diastolic than systolic, which I guess makes sense. These are a lot closer together than these. if we were to look at them as a frequency table or a graph, we could see that these have a lot more variation than the systolic ones. And that's the answer to this one. All right, well, hopefully this was clear. You can see this one has a much bigger series. There's more variation. Reach out. Let me know if you've got questions. I'm always happy to help. And take care. Don't freak out. Don't stress too much about stuff. Remember, it's just numbers. Why do we need them? We're always just trying to figure out one value or some value to give us the best approximation. Like, I don't care if you're trying to sell a house. I don't care if you're trying to explain a game. I don't care if you're trying to see like who's the best sports player. You always just want to whittle everything down to one value. If anybody wants to know how we can do that with stuff like computer science, we can do stuff called matrix manipulation. It's not like the movie, but like matrix manipulation, where I can take a 3x3 matrix. I don't care what it is. It could be 2, 1, 0, -1, 4, 3, 0, -2, 5. Not only can I find this thing's identity, but I can whittle this down into one number. And that's pretty much what statistics is. We're taking a bunch of values. We just have to figure out what the best value is. So the first one would be, remember how to do this? Yes. So you take the 2. And because I have the 2, that means boom, boom. AD minus BC is AD minus BC, which in our case is 2. 2 times 5, which is 20, minus a -6. So it's 2 times a positive 26. So this is 52. We got to minus the middle term and add the middle. Okay, so I know that probably seemed really crazy, but I'm basically just taking this thing and I'm going to turn it into. Oh, I lost the 1. Undo that. All right, I'll just draw another chart. Okay. Let's go with black. This is 2, 1, 0, -1, 4, 3, 0, -2, 5. Okay, so I used the 2. That means I knocked those 2 out and I have these to work with. So now I got to use the 1. So it's 1. It's the same thing, AD minus BC. It's going to be 52 minus whatever we get here. So if I have this one, I use the top row, and I use the middle column. So this is what's left. So AD minus BC. So it's going to be -1. -1 times 5 is -5. 3 times 0 is just 0, -0. -5 minus 0 is -5. So minus a -5 is the same thing as adding 5. Cool. And now we have 1 more to go. So the last one's going to be plus 0 times whatever. Well, if I have 0, it's going to be times this business, right? -1 times -2 and 4 times 0. But 0 times anything goes away. So plus 0. So this crazy box, and this is kind of how computer science works, taking very large sets of numbers. I did it with a 3x3, but you could do it with like 100 by 100. This whole thing, we can find that its determinant value is just a 57. And that's kind of what stats means. Stats mean taking a whole bunch of different values, but we just got to find the best. Is the mean the best to represent it? Is it the variance? Is it the median? Is it the range? Or in this case, is it the coefficient of variation? Like, what's going to be the best way to look at it? So it's probably like way too much information as usual. I just got done grading, so I thought I'd make one. But if you have questions, don't be afraid to reach out. I hope this was useful. If it wasn't, guess what? Reach out, read the book. There's also that guy, organic chemistry tutor, who's really smart. So take it easy and keep trying, keep working.